Hey Ron, glad to be here. So today actually I'm going to talk about why RAG is not enough. Before I get started, I'm going to put this slide. I put this slide a year ago as well at this moment, and I don't think a lot of stuff that changed since last year. And those problems, they still exist in Gen AI applications in production. We have super cool, shiny demos, but they are not yet production ready to be deployed into enterprises. We have a lot of non-differentiated businesses using GPT layer. And thanks to LLama-3, it gets even further non-differentiated. The problem is that, yes, LLM input size got slightly bigger, but they're also very expensive. And there are still trade-offs how to get the prompts and the context into the input. And of course, being in the vector database for the last year, the vector search does not actually solve the retrieval problem, and still a lot of issues there. And many of them can't handle many modalities. So before we get into why RAG is not enough, let's get back to what is RAG. And RAG is just a fancy name for enterprise search. What's happening is that you have a query, you get this query into an embedding space. Basically, you have a vector. You run this vector inside a vector database where you compare it to other vectors that already exist from the corpus data, and then you find the top 10 relevant ones and give this into the context along with your prompt to the LLM, and you get the final result. And what happened maybe last few years is that thanks to GPT-4 and large language models, those embeddings became so good, they bypassed more lexical search algorithms that we used to write, such as the BM25 that Elasticsearch is using. So that has been the biggest change. And then additionally, now you have a final LLM synthesizer that can summarize the data and give it as an output. But for context, they are, instead of being reasoning engines, they are more like journalists. They can summarize pretty good information. So the challenges that we have seen across enterprises, even before giving the insights and finalizing the output and the answers from the data, is actually bringing this data to the structured data sets you can train or run your LLMs. What we have seen is that you have many different data sources, such as Snowflake, could be Postgres database, running on your service, keeping your user information. Maybe you have a lot of PDFs, unstructured data sitting on top of your own S3. And now you also have a plethora of options to run embedding vector search or database to store them and then run search. And you have to cross-link across all these different 3 data storages. And then now let's say you want to train your own model on your own specific data. You have to copy this data to your local machine, do the training process and run this through loop. And you might have to also have a data scientist that's very specialized on building this data engine. And what we do differently is that we unify the 3 different data storages together into a single deep lake datasets that sit on top of your own S3, and then very efficiently stream this data to your pre-processing, training, and inference. In short, we do have computed storage isolation. We support multimodal data, not just vectors of multimodal data, but also text, audio, images, video, audio. In healthcare space especially, we have DICOM files that you can store CT scans or X-ray images, and you can stream, query, and visualize. But let's talk less about us and what we are doing at Activeloop, and what we think how the RAG future is going to look like. So this is very similar to what Tesla's data engine looks like, where on the left top you start with a data source. Maybe it's your corpus, your PDFs that sits on top of your Dropbox or Google Drive. And then the first thing you do is you put this into a vector database. In this case, I chose obviously Deep Lake, but you can choose any vector database there. And then next is you take this data and then plug this into your reasoning engine. And the reasoning engine is using large language models that are deployed and then can do answer on top of the context that you provide. However, so far when we call a RAG, there's no any feedback loop that's happening inside. There's obviously some folks call it RAG 2.0. Some folks tried other methods like raft. That's what we focus on this talk later today. But the main key thing is that similarly, what you had with self-driving cars is when you deploy the car on the road, you collect a lot more data, you find these edge cases, you then fine-tune back your model until the last mile that's nailed down that you can deploy this safely, and what we see with Waymos and Teslas on the roads. So there's one key piece that differentiates Deep Lake compared to other vector databases is the deep memory layer. Think of this as a very thin neural network. I wouldn't even call a neural network that sits between the vector search inputs and outputs. And what does it do differently is that it can train or basically try to transform the embedding space such that your vector search is more relevant, tailored to your specific data. Think of the following. You have a corpus data set that sits on, when it's embedded, it sits in one planet. And then when you have questions, those questions have a question mark. They are paused differently, not from your corpus data, and they sit in another planet. And what deep memory does is build a bridge between these two different embedding spaces or subsets of those spaces so that you can easily go and traverse from, let's say, question to the corpus land, and then from corpus land back to the question land. And the main key thing, it specializes based on your input queries that you have provided. Then there's also this method called raft. So what raft is done by Tianjun Zhang, sorry if I mispronounce the name, is following the following concept. So first of all, if you have an LLM and you ask a question, let's say it does have any connection to any vector database, no internet, it's just the LLM that has been trained on next token prediction across the whole corpus of the internet. Think of this as like kind of closed book based answering. And then RAG, or vector search plus LLM, is the open book where you have access to the data while you're answering the question. And access not just to the old data, but the relevant data. And then what Raft proposes is, can we actually go and fine-tune the LLM itself so that we can easily navigate the context when we get, let's say, the top 10 relevant corpus data and find the irrelevant ones. And the way it does is that you take the questions that you have, go and run a vector search, let's say generate 10 relevant examples for the specific question, and then now you feed irrelevant questions inside, answers inside, and then you teach the language model here to be able to disambiguate which element is relevant to that answer or not. And what we achieve here, which is very interesting, is the following result. So first of all, the left, we have LLama-3, 8 billion, and thanks to Meta again for releasing this awesome model without any context. So we take the COVID-19 data set, ask a lot of questions, and then measure what's the accuracy of those answers. So if you take a LLama-3, it will naively get 49% accuracy. Then let's take the same question and ask this to GPT-4, again, without any context. There's an improvement, yes, that's great. With number of parameters that inside GPT-4, we get about 65%. Again, this is no any chain of thoughts, no any reasoning on top, just question and answer directly. And then what we do here is that we take this small 8 billion parameter model, add a vector search. Again, there's nothing fancy. Take this vector search, add into the context, and now we have a boost of answers that's even better than GPT-4. Now, again, so 75% is not bad. Basically, you ask 100 questions, 25% of them are wrong. You definitely don't want to deploy this into any hospital, into any healthcare scenario that's super sensitive. We add this deep memory functionality here that whenever you run the vector search, instead of bringing the cosine similarity, which is the measure that you use to bring the relevant context, now we try to fine-tune these embedding spaces or train a deep memory metric that can bring the more relevant that has been fine-tuned on your own data set. And again, we are just using LLama-3, and it boosts the accuracy here. In this case, 7%. We have seen the training set about plus 4%. Sometimes there are use cases and applications that can go up to 22%, what we have seen. And this is like a significant improvement compared to what you don't have with Llama-3. And then what we do here is that we take the Llama-3 with a naive vector search, and then fine-tune the LLM synthesizer that gives you the final answer using raft method. And what we can see that there's a significant improvement that goes to 79%. And if we combine this both methods, then we get about 89%. Obviously, 89% is not enough to put this into production in any very sensitive applications. But what this gives you is the baseline that you can get started and then build your own RAG data engine and then start iterating and improving this accuracy to get 95%, or some use cases that really require 99% accuracy. So that's the big basis of it, and really thanks to Emanuele Fenacchi who did work on this project. And what I can do is I can very briefly go over the code. There's a lot of code to go over, and then answer any questions you have. Before get started, any questions you guys have? Okay, great. So basically I have two notebooks that I will quickly glance over, so I won't bore you much, and also the datasets that we can look over. So this one does the training piece. So what we do here, we first of all create the raft dataset. So the raft dataset is used for training or fine-tuning here the Llama-3. We define the dataset in Deep Lake. We create tensors each for this, for the question, the context, the answer, and the instruction itself. And then we add this into the Deep Lake datasets. So once the datasets are inside Deep Lake datasets, then we can quickly check the dataset in the UI itself. So here we have about 1,500 chunks that will be used for training the raft model. You can see here's a prompt that's inserted and the ground truth answer that is expected from the model to be answered. Then we load this is on using TorchTune. So Emanuele created a fork of TorchTune, which hopefully will be submerged to TorchTune, that can directly use Deep Lake and showcase the raft training inside. We download with a permission from Meta the Llama-3 8B. After the download itself, this kickstarted training or fine-tuning of the model. So you can see here it uses LoRa single device Deep Lake raft YAML file. Again, on TorchTune, you won't see it now, but you can go to the Emanuele's version of it, and you can find the training instructions there. This will take about 30 minutes, so obviously I'm not running now. Create a dataset, then what we do is interesting here. We use GPT-4 to actually generate questions and answers. And then the generation of the questions are actually based on the corpus data that we have from Core 19. What happens after this generation itself, we create the vector index and then embed the data as well. And we can go into the following Activeloop deep memory biomedical dataset. This is the corpus itself that you see. So you have the embeddings using, I think, just ADA2 basic model from OpenAI, the metadata relevant to that, and also the text dataset. So it's pretty simple, straightforward, structured dataset that you can run vector search on top. And then additionally, what we do is we also create, as we mentioned, we generated the questions based on the context itself. And now we have another dataset that has about 1,000 questions per each chunk. And then not just the questions, but also the ID, where this question, let's say in this case, is answering which corpus item is there. So basically, you create a synthetic dataset from the dataset that you already have if you don't have any questions. Usually what we tell to our users is that, hey, if you have a system that's already in production, your users are likely asking a lot of questions. Takes this data is much better than GPT-4 generated synthetic questions. And then there's the evaluation step, basically, which I have tried to create last minute here. Another much simpler model that will showcase what you need. So here, basically, we load the Hugging Face token, the Activeloop token, and OpenAI API token, load a question. This question is like, what caused the cluster of pneumonia cases in Wuhan. And then here's the answer. And a very naive example, I won't surprise anyone here, is we load the model itself, get the question, there's no any context, so you don't run any vector search here, and then you give it to the pipeline, and then you get the answer. And what becomes different when you use raft fine-tuned deep memory model is, again, you just, instead of using the default LLama-3 model, you can now use the fine-tuned version that Emmanuel uploaded as well. You can run the pipeline. Now, since we need to run the vector search, you need to also create the vector embeddings, load the dataset itself that we have just shared with you. And here's the core important piece is now you have the question, you take the question, obviously just run a vector search, gets the relevant examples, and put it into the context. And there's one key variable that we have is this called deep memory true. And what's happening is that in deep memory true is whenever you give the embedding is transformed into learned representation that increases the accuracy of the relevant context that is being brought back to the LLM context, and you get the final answer. So hopefully didn't get into too much. But yeah, so this has been a basic example of how you can improve your own RAG pipelines, going from using like 8 billion parameter model that's can be deployed in production at enterprises and getting overpassing GPT-4 accuracy here. Thank you very much. So we haven't yet on this one example, we just got the results yesterday, run with chain of thought. I think the chain of thought will improve the LLM reasoning piece, but it's still the vector search is the same. So if you have, let's say, not relevant context, then the results, so with chain of thought, you sometimes have the butterfly effect, where one small error that gets propagated through the chain that you're building. Then the likelihood of having the repeated elements that are wrong in the context is potentially increase. This is just a hypothesis, right? We have to run the experiment and see and make it worse. So what was the next step here that what we were discussing is that in addition to running chain of thought, you also run prompt optimization. So those are the two steps that are left, and hopefully push the last accuracy way higher that passes for some applications to be deployed. But we haven't, to be honest, tried it yet. And take these results with grain of salt. This is very specific to this data set, and try run on your own data sets and try to get those benchmarks and comparisons, and not just look into a single accuracy metric, but there are many other RAG metrics that people meet, including recall or others, you can precision, etc. We have a customer, Moai, they're deploying this to one of the largest hospitals in Brazil, I think Einstein Hospital. And what they do is that it's very remarkable. They take a lot of protocols. So whenever you, let's say a physician prescribes anything, they actually have to follow a protocol and then put these protocols into a vector database. And then when a patient asks a question, they quickly match this result to the protocols and bring back to the final LLM synthesizer. So here you have physician in the loop, so it can actually detect if there's anything wrong or bad. But what we have seen is if you specialize in a very specific use case, which is this protocol search, then you can get the LLM answer. I don't want to put numbers. I think they have their own numbers, but it's 90+% accurate for very domain specific use cases. So that's one example that's publicly we can talk, but more, I think currently I will hesitate and make sure that you have full understanding of how this LLM works before you put this into a hospital. And what we have seen actually way more use cases in medtech or life sciences verticals where you don't have this deployed in a mission critical scheme. So I wouldn't deploy now in mission critical use cases, but for this kind of back office work, this can really help. Also another use case, which is very, very apparently growing, is the transcription. So whenever a patient talks to the physician, taking the doctor notes, this is I think now is deployed in many, many hospitals. So these are some of the use cases you can use it now. in healthcare, you won't use the biggest superpower of LLMs is the hallucinations, but you need to pick such use cases where they actually are super powerful. For example, like legal space. In legal space, whenever you're changing any definition inside a contract, there's like a big, you can have like 3 lawyers arguing differently with each other, which definition is great. And I have seen it myself, like when you go to a lawyer, one lawyer say that you have a cancer, and the same lawyer with the same definitions can say you don't have a cancer. Cancer is an example from the healthcare, but there's like a big problem in the contract itself. So I think the LLMs and their hallucination superpowers are super domain specifically used there. And we have a customer there, Hercules AI Zero. They're using Deep Lake, deployed this in the lawyer firms inside their own data centers. So there's like the data sensitivity is a big issue there as well. So anyway, the legal space, and I can't wait to automate the lawyers. So I think that's a big space that will be disrupted. And every text in and text output use cases with human in the loop. So again, there's no any full automation there. I think we are not if 5, but more than 10 years away from having fully automation. But you can make now, like let's say, lawyers 10x more efficient by enabling them with LLMs. The way I think is, it's if you read the contract, it's very similar to the code. Like when you program, right? You import, Deep Lake, import NumPy, and then run computation, or you import your local library that you have built locally. It's very similar to the contracts. They can import, let's say, California law, then they can import your company law, and then start building their own definitions and thesis, and then make a contract at the end of the day. So I would say it will be automated even faster than writing the code, but you need a lot of human-in-the-loop lawyers to be able to do that. And lawyers who are open-minded, and I know a lot of them, they actually want to embrace to automate a lot of work there. I'm not an expert in LLM evaluations, and I would love to see an expert in this field. There are a lot of benchmarks, right? But those benchmarks can be easily tricked over if you overtrain those models on the training sets or the validation sets. So nobody knows what happened with the data sets that have been fed into the most recent models. Do you have also these arenas that can do more like dynamic evaluation of models? We have companies and partners on our side that are building evaluation tools. One of them is Weights and Biases doing Weave. We have another classmate of mine from my undergrad doing Context AI. So a lot of folks, smart folks, are working in this field and trying to build the de facto standard for evaluations. But like, since you're operating in text space and it's like super hard to evaluate text, it's a hard problem. It's like the same as like when you make up exams, and then like I did myself when I was doing my PhD at Princeton. I did create an exam for students who are taking neural network course, and we wrote a question. That question could have been answered 10 different ways, and all of them were right. I remember there's one question that's interesting to remember as well. We wrote like, hey, can you come up with a neural network on the paper that can solve this and the and/or problem, nor problem using logic. So a lot of people had subset of them had diagrams, subset of them just wrote the weights on the papers. So what we did is that we created the simulation of a neural network in Excel sheet, in Google Sheet, and then we just transfer the weights and then start normalize the answer and then start evaluating if this is correct or not, because there's many branches you need to check. So the moral of that is that it's very hard to even evaluate human answers, and if not, like the LLMs themselves.